Alright, we're now going to start chapter 13, and we're going to spend 3 days on section 1, the fluid states of matter. The first one, our objectives are to demonstrate an understanding of the concept of what pressure is, and then we want to define the Pascal and be able to calculate pressure and force. You can see your assignment there. In class, we're going to go over the test. So 13.1, pressure, the fluid states. Fluids are defined as any material that flows and has no definite shape. When we think of fluids, we typically think of liquids. Because you can pour water out of a beaker into something else, it flows down a ramp or it flows from one vessel to another. But gases are also considered fluids. So anything that flows and has no shape, gases definitely have no shape, and we'll demonstrate that we can pour gases as well, especially if they're heavier than air. Pressure is defined as the force per unit area of a surface. And the force needs to be perpendicular to the surface. If it's not, we could actually resolve that into the perpendicular component to find the force that's perpendicular, but for this class or this test, we will just assume the forces acting on them are always perpendicular. Here's your equation for pressure, force divided by area. Pressure is a scalar quantity because it really acts every direction. We can explain that in class. If you're talking about air pressure, I've got the pressure is pushing down on or around on my body in every possible direction, so there really isn't a defined direction for that pressure. If I'm talking about the pressure I'm exerting on the floor, well, yeah, my force is downward, so you could say your pressure is down, but typically we think of it as a scalar quantity. We measure force in newtons in the SI system and area in meters squared. The SI unit for pressure is the Pascal, so 1 Pascal is equal to 1 Newton per square meter. So if we're going to use this equation, our force has to be in newtons and our area has to be in square meters. So, how does the kinetic molecular theory explain gas pressure? Well, kinetic means movement, so we're going to talk about the movement of particles at the molecular level. We know that gases are made up of small particles. We know that these particles are widely separated and they're in constant, rapid, random motion. Our kinetic theory from chemistry says that they make elastic collisions with each other and the walls. So they're flying around all over the place, every possible direction, so they're going to run into each other and the walls, and when they do, when they collide, they are elastic. And if you remember, elastic collisions are such that do not lose any kinetic energy. So it hits another particle, it's going to bounce off with the same kinetic energy that it had before. And the forces that are exerted by these collisions will result in the air pressure, or pressure. So you have forces, they're acting on little areas, and they run into the wall and such, and that force over area can give you pressure. Atmospheric pressure is the pressure exerted on the Earth's surface by the atmosphere. there's about 10 newtons of force on every square centimeter of the Earth's surface. And that's due simply to the weight of the air in the atmosphere. This converts to around 1 times 10 to the 5th newtons per square meter. So 100,000 newtons of force act on every square meter of the Earth's surface, and that's just the weight of the air. One other conversion I'm going to add that's not an SI unit. This is around 14.7 pounds per square inch. That's something you can maybe visualize a little bit more. If you would take 15 pounds on every square inch of your body, that's how much air is, that's the force of the air pushing down on them. So if we look at Earth, we know the Earth is surrounded by an atmosphere. If I just look at 1 square centimeter of that Earth, or actually better yet, let's call this 1 square inch, and we take the air that's all above it, the weight of this column of air is around 14.7 pounds on every single square inch of the Earth. We're going to cover one principle today, and then we'll talk about a couple others tomorrow. We'll have a demonstrator, a bunch of demonstrations in class when you actually get there. The first principle is called Pascal's principle, from the same scientist Blaise Pascal. And that principle says any change in pressure applied at any point on a confined fluid is transmitted undiminished throughout the fluid. Any change in pressure applied at any point on a confined fluid is transmitted undiminished throughout the fluid. The other thing that's interesting is that the shape of a container has no effect on the pressure. The only thing that matters how much pressure there is the depth of the fluid. And obviously the type of fluid. If you had a more dense fluid, it can exert a greater force, therefore greater pressure. But if you have a thin tube, a thick tube, a swirly tube, doesn't affect the pressure. The only thing that affects it is the depth or the height of the liquid in that container. Pascal's principle is used to help explain, well, we can have the example of toothpaste. If you have a brand new tube of toothpaste, you've got yourself a confined fluid, and it doesn't matter where you apply the force on that, the toothpaste is going to come out of the other end. So you apply a pressure at any point in that toothpaste, in the top, the middle, or the bottom, that pressure is transmitted throughout, toothpaste ends up being forced out of the open end. This also leads to a real-life application of hydraulics. Here's how this works. Let's pretend I've got a piston here. And I have a larger piston head over here. And this is all filled with some type of fluid. So these pistons can move up or down. On top of this one, I apply a force of 6 newtons. And let's say that this has an area of 1 square meter. And this one is obviously larger, let's call it 20 square meters. The question is, how much force can the larger piston now lift? Well, I've got a force here on the first piston, and this is an area on the first piston. Therefore, there's a pressure there. So the pressure on the first piston is equal to F1 over A1, or 6 newtons over 1 square meter. So the pressure here is simply 6 pascals. That's how much pressure this fluid is pushing downward on that piston. Well, Pascal's principle says any change in pressure applied at any point is transmitted undiminished, which means if there's 6 pascals of pressure being pushed down here, there is 6 pascals of pressure being pushed on the larger piston. So to find the force on the second or the larger piston, that's pressure of the second one is F2 over A2. I know the pressure is the same, 6 pascals. It's undiminished throughout. I don't know what this force is, so my area, which was 20, goes right there. I can cross multiply and find my force would be 120 newtons. So by simply adding a force of 6 newtons here, I can lift 20 times that, 120 newtons. This is how those lifts in car dealerships work when you need to get your oil changed. You apply a small force, but that gets magnified. In this case, the mechanical advantage is around 20, because you're getting 20 times the force for what you applied. Since these pressures remain the same, Pascal's principle is often written this way in terms of equations. F1 over A1, which I know is the first pressure, that equals the second pressure, which is F2 over A2. And this is something that you should go ahead and put on your card. If we had that, we simply could have said 6 newtons over 1 equals F over 20, cross multiplied and divided, and gotten 120 for our answer also.